Okay, so I think we'll get started. We just have a couple things to finish up on lecture 15, and then we're going to move on to lecture slides 16, which are in the box. And I uploaded a lot of the last PowerPoints that I have for class, including some lectures on complex structures, on conductivity, some other tidbits in there just to finish off some folks' interest in class. So we'll try and get through all the slides, although it'll be a push. So I encourage you to just take a look at what we're going to cover, I guess, next week. So we only have 2 more lectures after this one. And if there's anything that I'm missing or anything that you want to know more about, just let me know and I can sneak a couple things in at the end. So we should have a pretty good idea of how the lectures are going to wind up. And of course, they'll be posted on YouTube as well, so you can review anything that you need. And I've gotten some good questions on the final project and presentation, so keep those coming. Again, the more work you do now, the less work it's going to be during finals week. And so please solidify your plans and start to get your presentation materials and keep writing on that paper. So before we start talking about slides, are there any questions or discussion points that people want to talk about? All right, well, we'll get started with the discussion, and then please unmute yourself and chime in if you have a question, or I'm looking at the chat. So if you have something you want to talk about in the chat, just put something in there and I'm happy to address it. So we ended up here last time talking about manufacturing different components with additive. And as part of manufacturing, we talked about safety. And of course, there are some interesting headlines in terms of the safety of desktop printers in a closed environment, in rooms that don't necessarily have great ventilation. So that's something to remember. And what we learned about was that not only are there the semi-volatile compounds or the fumes per se, the melting plastic that you can smell, but there's a lot of particles that come off of these material extrusion AM printers. And that's because we're shearing a hot polymer through that heated liquefier, and that's going to create atmospheric particles. And those particles are pretty bad for you. So this cool paper measured all those particles and showed that the particles persist even when you stop 3D printing. And then they compared a few different materials, a few different temperatures, and you can see that higher temperatures give you more particles in their analysis. And so this is interesting because we talked about road adhesion a lot in material extrusion AM. And of course, in order to get better road adhesion, it's helpful to have heated underlayers or to have high temperatures in order to get those polymers, those roads to fuse together. So this is something that needs to be addressed in industrial scale printing, especially since we have regulations like OSHA and worker safety regulations that need to be addressed when we're doing manufacturing. And so lots of industrial printers now will have enclosed printing volumes. They'll have built-in ventilation. Some printers have HEPA filters on them, so they're not putting particles out into the room. And this paper just addressed material extrusion AM. Of course, we have stereolithography, where we're using volatile chemicals or reactive precursors. Those resins aren't necessarily the best thing for you. We've got polymer powders, and we talked a little bit about powder safety in SLS, where powders can be explosive, and also powders are particles, so they're not good for you. And so there's lots of safety issues that we need to think about with additive manufacturing as we think about large-scale additive, using additive in an industrial environment. And of course, if you have a printer in your house or a printer in your basement or garage or something, it's also, it'll be important for you to keep that in mind so you can at least protect yourself as well as possible when you're doing at-home printing. Because everyone likes to stick their face up right next to the printer and see what's going on. That might not actually be the best thing for you. So rules are coming out for 3D printing. So this is from Occupational Safety Magazine. And so the people who are safety professionals are really starting to think about how is additive manufacturing going to influence workplace safety, worker safety, and environmental safety and health in industrial environments. And so this is something that you can think about, especially as you start to move from doing research in an academic lab or projects at home to working in an industrial environment. And so there's lots of articles like this. So this article is talking about desktop printer safety, but again, what we learn on the desktop or what we learn at home, people are working hard at translating to real manufacturing environments right now. So are there any questions or comments on that? Anything that people want to discuss? All right, well, I think that's something that you should all remember, and you can go look in your academic labs and see how well you're taking care of printer safety in academic labs, and make sure that that's something that you keep your eye on, especially as you're doing the lab work and as you're exposed to these things. It's just like handling any hazardous material or any toxic substance. You want to have some good awareness so you can mitigate the risks. All right, that's lecture slide 15. So now we're going to just talk a little bit about applications, and we've hinted and discussed some big application areas and talked about markets in those application areas. And so we're going to walk through examples in biomedical, in aerospace, and automotive. And those slides are all up on the box for you to see, so you can see what examples we're going to talk about. If you're interested in some examples and not others, please let me know. Or if you're interested in more detail, let me know as well. But I want to give you an overview of where all this polymer and composite additive manufacturing knowledge is going to be used in certain market sectors. You know, of course, there's lots of places where additive may be helpful: apparel, oil and gas, water treatment technologies, you know, you name it. Some industry is looking at additive as in terms of some aspect of their business. But I want to cover the major ones, because these major ones are where additive is gaining an industrial toehold that will allow dissemination across other manufacturing sectors. So lecture 16 on box is all going to be about bio applications in medicine, and we've seen some of those, and I'll round that out a little bit for you in this lecture. So just to recap, if we think about where additive is used in different products and industry, we can use this rubric right here, or this 3-axis model of manufactured products. And so what's interesting is that lots of biomedical devices are customized for the individual. In a lot of cases, you're doing mass customization. Every hearing aid is a little bit different because everybody's ear or the shell is a little bit different, and they're all custom fit. Same with braces, same with dentures. And so there's a lot of mass customization that's possible. And also in biomedical devices, we could be really interested in complexity. And so how do you make very complex things, well, including all this customization? And in some cases, also, you only need a few products. So rather than braces, if you're doing a very specific cranial implant, or if you're doing a tracheal implant, say for infants, you only need a few of those. You know, there are lots more people that get braces than get tracheal implants. And so that's something to keep in mind. So we can place different biomedical products in this cube and think about how additive manufacturing plays in this sort of environment. We also talked about this last time, and so as additive manufacturing develops, it's going to get a little bit cheaper. but it's going to get a lot faster. And so rapid deposition is also a place where additive manufacturing has room to grow. No one complains that additive manufacturing is too fast. And so technologies that decrease the cost of additive are important, but a big part of decreasing cost is just making it faster and faster to amortize the part number or the number of parts across a certain machine. Okay, just a couple review slides here. We've seen this before, so you can think about these things. And we're going to talk mostly about healthcare and medical in this PowerPoint slide, and we're going to cover the other things later, but custom implants, custom prosthetics, perhaps manufacturing human organs. We'll talk just a little bit about that. That's a job for advanced polymers. Bone implants, body parts, hip joints, skull implants, robotic hands, things like that. And these are some of the large-scale benefits gained by doing additive manufacturing in the biotech and healthcare space. And we'll talk about specific examples, like I said. And just as a reminder, we're going to include dentistry and dental technology in with healthcare. And dentistry and dental technology is a big business on the order of billions of dollars. So it's not quite as big as trillions of dollars in automotive. But if you've ever paid for a set of braces, or if you've ever gotten yelled at or yelled at someone for losing their retainer, you know that dental implants and dental appliances are expensive. And so because dentistry and biotech and healthcare products are generally high cost, that gives additive manufacturing a way to enter the market because there's expensive components in these devices and they're relatively small. So retainers are not very big, hearing aids are small, hip implants are pretty small. All of those small volume products can be handled in a lot of AM technology that exists out there right now. We will talk about additive manufacturing of airplane wings. Those are big. Not many printers can do that. And so making larger components is a barrier for additive. But a lot of these small things in tracheal implants, in healthcare and biomedicine and dentistry is handleable using current additive technology. And so that's provided a way for additive to gain market share in these early adoption type environments. So there's some nice websites on this. And so this is one of the articles from Popular Science, additive manufacturing from implants to organs. And so right now, people are doing additive manufacturing of hip implants and other biomedical technologies. And the vision is eventually they'll be able to 3D print a liver or 3D print a heart or 3D print something that's a scaffold for growing a new organ from it. So we'll go through some examples like that, but that's really where things are headed. Also, 3D Hubs has a really nice website on this. Let me click over to the website so we can all take a look at it. And so this is the 3D Hubs medical 3D printing applications. And this is interesting because it goes through some applications that and some requirements that we haven't covered so far in this class. So we've talked about anatomical models. So this is a model, I think, of a brain or something like that, showing all the blood vessels. And it gives surgeons a way to look at internal body structure without having to use cadavers, they can practice surgeries without having to practice on living people. And so 3D printing has really found a home in terms of production of these anatomical models. So there's some things here and some pictures. Okay, that's great. One of the interesting things that they bring up in this webpage is they talk about the ability to sterilize polymers. And of course, if you're working in a biomedical environment or you're working in a hospital or you're working in medical technology, sterilization is really important. So whether you're using gamma irradiation, whether you're using steam autoclaves or other types of sterilization like ethylene oxide gas or other plasmas, different polymers like ABS or polycarbonate or polyphenol sulfone are, these different materials have different susceptibilities to whatever sterilization technology you're interested in. And so hospitals use a lot of different types of sterilization. And so it's important to think about materials compatibility, not only in the biomedical context, is this polymer compatible with skin contact, or is this polymer compatible for an implantable device? But it also needs to be sterilized using whatever technology is used in the hospital or that the surgeons are using before they put the implant in. So this is one interesting thing that you should think about. Also interesting because these are generally custom implants. How do you generate data for the shape? So we know in general the shape of a hip socket, or in general the angle that the socket approaches the femur, but a lot of those things are slightly different for different people. And so medical imaging has come a really long way with the advent of MRI, magnetic resonance imaging, which is like NMR in 3 dimensions, or CT scanning, which we've talked about, which is X-ray computed tomography or CAT scanning. And so hospitals are really equipped to do this advanced imaging to generate custom anatomical models, which from that you can generate custom implants, you can modify the design. And we see that with medical technology. If we get to the dental aligner video, they have a really awesome video showing how they do an optical scan of your mouth and are able to make Invisaligns that are programmed exactly for which ways to move your teeth. That's very interesting. And so this sort of synergy of medical imaging and custom imaging of people really has dovetailed nicely with additive manufacturing technology, where you can do customization for individuals. All right. And then 3D Hubs lists some common applications: surgical learning tools. So how do you plan surgery? That's very interesting. Surgical guides and tools. So if you're going to get a root canal, or if you need an implant drilled, you'd really like to have a precise guiding of that drill. So they often use these drill guides or tools. And so this is also a big business. And this, again, is not necessarily 3D printing the product, but 3D printing a tool that helps you make the product, in this case, an implant or something like that. And so having custom surgical guides is helpful. Let's see, what else is there? Okay, implants, that's great. Prosthetics, and of course, hearing aid, the hearing aid example. So they go through some limitations. Again, there's a case study on here from 3D Hubs, but if you're really interested in thinking about all of the different ways that additive manufacturing is contributing to biomedical science, this is a good resource. Oh, let's make sure my PowerPoint comes back here. Hopefully it will. Oh, maybe I'll go back in. All right, the internet might be feeling slow in my house today, but it'll come back. So anyway, I encourage you, if you're interested in biomedical and healthcare space, to take a look at what's out there. It seems like there's a new innovation every week in additive manufacturing in this space. And I want to talk about some very specific examples that are germane to polymer and composite additive, but additive has a lot to say in general about healthcare. So there's this article on hearing aids. And so they talked about, does additive drive down costs, or does additive give you better functionality or expanded possibilities? And so we often discuss technology adoption in terms of, well, it's lower cost, so we should do it, or there's a business case for this. But there's also a business case for additive complexity, better functionality, higher quality of life, expanded possibilities. Old style hearing aids were heavy. They didn't have great acoustics. They were uncomfortable to wear sometimes. But really, hearing aids are still expensive. And so additive manufacturing didn't necessarily bring down the cost of hearing aids, but they really provided additional functionality to really improve people's quality of life. And that's also an important area that additive can contribute to, because if biomedical implants or dentures or hearing aids or braces or what have you are more comfortable, even though they're still expensive, perhaps you can get better adoption of these technologies because additive gives you something in the product that you can't get otherwise. So that honestly depends on the market. Sometimes people will pay for expanded possibilities and better fit, form, and function, or better comfort. Sometimes they won't. And so this is where you really need to know your market and figure out who your customer is. You know, sometimes an automotive company is going to say, I'm not going to pay 1 penny more. I don't care how good it is. I want something better, and I want it cheaper than the incumbent. And so you're not going to be able to make the case to Ford that your 3D printed bumper that costs twice as much is worth it, because they're not going to be willing to pay that price. But what the biomedical industry has discovered is that when it comes to people's health, people's comfort, people's quality of life, they're willing to pay a little bit more. And so that's why additive has made good inroads in this industry, because there's been a way to internalize the cost of additive into these products. So I suggest you check out some of these websites right here if you're interested in learning more. So the dental market is big. The entire dental market is predicted to be $37 billion. So tens of billions is not small. And the compound annual growth rate is predicted to be north of 5%. Again, when this website was made, they didn't know about global pandemic in 2020. So who knows what it's going to be. I've been avoiding the dentist in the last 6 months, but that will eventually go back to normal. But anyway, $37 billion is a big market. So if dental can capture part of that, that is all of a sudden billions of dollars. And of course, we know that the additive market is growing as well. And so we see that additive technology is intersecting a lot of these high dollar, high value, and high growth rate industries where adoption of new technologies is easier. So in 3D printing in dentistry, if you look at Carbon's webpage, if you look at Envision Tech, if you look at 3D Systems and Stratasys, all the big players in additive are interested in participating in the dental market because there's a lot of things to do there. And so by 2020 or 2021, if the entire dental space is going to be $37 billion, perhaps additive will be 10% of that, or $3 billion in the next year or so, depending on how things shake out. And so you see how things are broken down here in terms of the total dental 3D printing market opportunity. So you've got services, selling dentures, selling aligners, you know, the doctor's fees, all of the service that you provide to sell the hardware. So you buy a printer, you buy some materials, you buy some software, and then you can sell dentures and you can sell braces and other things like that. So there's a lot of room there. So the blue bar at the bottom is $500 million worth of dental printers in, let's see, 2024. So that's an awful lot of printers. That's an awful lot of carbon printers or Formlabs printers. And so if you're interested in selling polymers or printers into the dental market, there's money to be made there. And we're seeing that. We're seeing adoption of printing technology in the dental space by dentists and also by factories that make things for dentists, or local manufacturing that makes things for a number of dentists' offices. One of the big, well, like I said, all the big players in 3D printing of polymers and composites like Carbon and EnvisionTech, they have their dental divisions. And so if you follow the 3D printing news for these companies, you see a lot of things about 3D printing. And these are all the different sorts of appliances in dentistry that you don't think about very much. Surgical drill guides, denture bases, these bonding trays that they used to put that pink stuff in. That's not awesome. Castable crowns, things like that. So there's all sorts of opportunity there. Any questions so far on dental? Any questions on dental market or how this relates to what we've learned in polymers and composites? All right, so it turns out that dentistry has been familiar with polymers and composites for a long time. So fillings used to be mercury amalgam, or fillings used to be metal, low melting point metal, but recently in the last 10 or 20 years, all fillings have generally been UV polymerized porcelain filled acrylates. And so they use titania and zirconia and other ceramic fillers with a UV cured photopolymer. And so dentists have been used to this new technology. They've been used to polymers and composites, even though they generally don't know the details of the material. But these same sorts of technologies that have been used for fillings can now be used to UV polymerize teeth or UV polymerize implants or dentures. And so that's where the industry has really innovated in this area. So this is just one example right here from EnvisionTech. And so they're using the EnvisionTech Ultra printer. So you can look up what that is, but it's an SLA printer that we've talked about before, and this RC31 material. So you can look up what that is on EnvisionTech's website. And so now they're printing these teeth based on making digital models for making braces or dental correction or something like that. So there's a lot of interesting applications in dentistry, even so far as making a model of someone's mouth in order to build the appliance. Same thing here for Formlabs. And so they make a model of a person's jaw, and they can make a retainer from that, or they can make a line or aligners from that. So these plastic braces, those are called dental aligners nowadays. And so this one anecdote from this dentist, he or she used to charge $35 for a single retainer, and it took 3 weeks to get it. Now with a 3D printer, he can do a retainer for $2 in less than 3 hours. And so dentists are starting to adopt this technology right in their office rather than having to send out for these appliances to be made. So again, there's lots of case studies on the different manufacturers' websites. I suggest you check it out. And so we will look at a video about this in a couple slides here. But this idea of optical scanning or intraoral scanning, basically it's a laser scanner for your mouth. And then Preform is the software that's used in the Formlabs printer to make a model and send it to the printer. And then he can print this right in standard resin. So he's printing a model of the tooth. That gray stuff is, or it's a little bit better right here. The gray stuff is a model of someone's teeth. And then what he uses is he uses a pressure former to vacuum form a retainer onto the model. So in this case, he's not printing the retainer, or he's not printing the dental aligner. He's printing the model of the mouth, just like this or just like this, in order to do the shaping of the retainer. So he's using a vacuum former over the model in order to get the dental appliance that they're looking for. And so we talked about this before, where instead of 3D printing the package that you need or 3D printing the component that you're going to sell, you 3D print a mold and then use vacuum forming or another type of high-speed manufacturing in order to get the component you want. Just like the customized chocolates from Hershey, they're not going to cast chocolate in a 3D printed mold, but they'll 3D print a mold and then use vacuum forming to vacuum form food grade material over that mold so that then they can cast their chocolate in a food grade mold. So exactly the same process, just a very smart type of workflow in order to get this retainer or aligner out of approved materials. And so you don't have to figure out, well, how do I print the metal wires and the plastic, and what type of plastic am I going to use? And it's going to be really hard to invent plastic that is useful for retainers. But if I just 3D print a custom model of a person's teeth and then use my traditional manufacturing materials and techniques in order to make this appliance, I don't have to invent any new 3D printing technology. I can use what I have already. So that's an interesting difference than having to additive the products, as we've discussed before. And so this is just another article from Forbes talking about how 3D printing is important to Align Technologies. So Align Technologies are the dental aligners. And so they're creating not only 220,000 products a day, that's a heck of a lot of dental aligners, but they're doing mass customization where they're creating 220,000 custom-made products each day, just like we saw with hearing aids. And it's really amazing how this works in a manufacturing environment. So I'm going to play this video right here from Align. So they're talking about what they do in order to make these dental aligners or these clear braces. And so just like hearing aids, this has been a huge win for the additive manufacturing industry, contributing to custom biomedical or dental devices. So let me see if I can get YouTube going right here. All right. Let's see if this works. Looks like a tooth video with smiling people. Here we go.
A great smile can transform a person's life. At Align, we create technology that helps people have the confidence to take on whatever's next. Invisalign has really revolutionized the orthodontic industry because they have a completely digital way of doing orthodontics. It's convenient, non-invasive. It allows you to live the life that you want to live, and it's a much faster treatment than what wires and brackets offers.
We leverage the power of technology to create great smiles and a brighter future for millions. By integrating digital imaging, 3D software, and shape engineering, together with world-class mass customization and the world's largest 3D printing operation, Align transforms less than an ounce of high-tech polymer into a 21st century engineering marvel. Whether it's clear aligners, digital scanning, virtual treatment plans, or software apps that help patients visualize their new smile, our technology and processes deliver a better-than-braces patient experience and effective treatment outcomes. It all begins with a 1-minute scan. The iTero intraoral scanner replaces goopy physical impressions with a precise 3D digital scan. Using Align's proprietary software, our dental technicians use the scan to create a virtual treatment plan customized for each patient. Doctors can modify the treatment plan to meet their patient's specific needs, from crowding or gaps to deep bite or overbite, pre-restorative alignment, and most everything in between. A series of unique, shape-engineered aligners are then manufactured using proprietary 3D printing technology. Built on a foundation of over 430 patents, Invisalign aligners use 3 unique smart technologies. Smart Track aligner material is designed for optimal control of tooth movements and on average enables faster treatment than braces. Smart Force attachments and features designed into the aligners deliver the precise forces when needed to achieve more predictable tooth movements. And Smart Stage technology, programming each tooth movement in a certain sequence at the right time to achieve optimal outcomes. After 20 years and more than $1 billion in revenue, Align is the undisputed leader in clear aligner therapy.
We're the only company in the world that has an orthodontic database of 5 million patients, and we use machine learning to mine that data to really understand how we can do orthodontics better, how it can be faster and more convenient for both doctors and patients.
Our goal is to make it easier for millions of people around the world to enjoy a great smile. We're doing this by expanding our business globally and making our product available in more countries, adding new treatment planning and manufacturing facilities to support doctors locally in all of our major regions, developing new products for the most complex orthodontic cases, especially teens, and working with dentists and making it easier for them to offer simple teeth straightening solutions along with high-quality dental procedures and restorative care to all their patients. And we're raising awareness with consumers, especially teens and their parents, to ensure they ask for Invisalign, the orthodontic brand more teens prefer over braces.
I now have teenagers that come to the practice asking for Invisalign because they don't want to use, they don't want to have brackets and archwares anymore.
For us, it's very nice because we don't need to tell the patients, you should use Invisalign. They say, I want to use Invisalign, and that's magnificent.
With over 1 billion people in developed countries, we have the potential to help 300 million consumers gain access to smile-changing technology that can only be done digitally. We're committed to moving the industry forward, constantly innovating, always improving the world's most advanced teeth straightening technology and the way people think about their smile.
What drives employees at Align is the opportunity to give patients a better future with a better smile. That's the foundation of what we do.
Okay, well, that's not necessarily commercial for Invisalign, but you can see how important additive manufacturing is in all of those steps. So you have the digital visualization, you have the scanning, you have the computer-driven design of whatever component you're going to make. You saw a lot of stereolithography printers there, the big ones that had a bunch of different aligners right on them, just like we saw with the hearing aid shells. And so it's a really interesting way to think about industrialization of additive manufacturing and all the software customization, all the different steps that are needed in order to really revolutionize this business. And so that's very interesting. Now, if you've ever done a lot of 3D printing, you know, again, how do you make 220,000 of something custom? And so if you have one Formlabs printer, you're not going to be able to do that. But the printer companies are thinking about these manufacturing challenges. So how do you take a figure 4, which is a stereolithography printer from 3D Systems, and how do you integrate a number of these printers together? So you have a bunch of printers, you have a place for post-processing, and then you have a control unit that coordinates all of these. So it's not very scalable if you've got 10 technicians standing in front of 10 different printers just waiting for things to happen, because it takes time for 3D prints to come out, takes time to post-process them. And so there's a lot of really interesting hardware innovation in terms of how you industrialize additive manufacturing in a way where you don't have to be standing there and watching the printer the whole time, like we do in the lab, or like you've done before if you've ever 3D printed anything. So if you're interested in hardware development, this is one of the things that the companies are working very hard on, in addition to perhaps new printing technology and the next generation of some of the printing technologies that we've talked about in this class. Any questions or comments so far? All right, we'll keep going. There's a lot of these videos out there showing how additive manufacturing is changing whatever specific industry you're interested in. There's one for movie props. There's one for custom manufacturing for small scale businesses. There's one for food and chocolates like we talked about. And so if you're interested in seeing more examples of this in the real world, there's a lot of resources out there. And now with this class, you have some knowledge about what polymers they're using, what additive technologies they're using, and what the future might look like in terms of additive manufacturing of polymers and composites. Another really cool example is this from Oxford Performance Materials, or OPM, and they're specifically using PEKK, so that's polyether ketone, as we've discussed before. Also, this is a relative of PEEK, polyether ether ketone, which is just a variant of that. But Oxford Performance Materials has their own grade of PEEK, and they've been looking very specifically at cranial implants and other types of neurological implants. And they have a really cool video that was done on their company at this link right here. So we're going to watch one more video today on this. And now this is made using SLS. And so they have some really nice SLS pictures in this next video we'll look at. So they're talking about how they design these, how they do custom imaging, because of course, if you're going to do a cranial implant, say for a skull injury, you need to know exactly what it should look like, and then how to print it and finish it, etc. So we'll switch over to this video if I can grab it. I think it's this. All right, here we go. And OPM, I guess, is in Connecticut.
Like something out of a science fiction movie, the new age of manufacturing, where you simply pour an ingredient into a machine, and some 12 hours later, out comes your product. It's called additive manufacturing, or 3D printing, and it's happening here in South Windsor, Connecticut, at Oxford Performance Materials, a plastics company on the cutting edge of technology, founded in 2000 by Scott DeFelice.
And when we started, this is what we did. We had this machine, and it's making strands of plastic that are being cut over here.
We started out as a raw material company, so we were selling it primarily into two markets, into aerospace and into biomedical.
So what we've got here is one of our early products. This will typically go to a machine shop who will then maybe make a dental part, maybe they'll make a spinal implant.
OPM also makes its own products by pulverizing the raw plastic into a fine powder.
It's structurally strong, It's lightweight, it's biocompatible, it's chemically inert, it's radiation resistant.
Turns out it's perfect for airplane parts as well as orthopedic implants.
So this is a typical cranial prosthesis.
OPM's first product, the skull implant, approved by the FDA in 2013.
The surgeons love it because it fits so well. You see it has some holes in it. That's so blood vessels can grow through and keep this tissue on top healthy.
I would suggest that, you call, make an appointment if you can.
Neurosurgeon Dr. Inam Qureshi's been performing surgeries for nearly 20 years. He's used several different types of cranial implants.
The most common diagnosis that requires this sort of thing are patients who have had a traumatic brain injury that required removal of their bone to allow the brain to swell. She has a brain abscess and she actually may need to have her bone flap removed. The main concern we have as surgeons is providing adequate protection for the patient as if it's their own bone.
Dr. Qureshi says the typical wait for an implant is 4 to 6 weeks. And that's what has him so intrigued by Oxford Performance Materials' new product.
Once it's designed, once we have an order, it's 5 days.
It is so much more beneficial for the patient to have that kind of turnaround time. Because normally when bone has to be removed, they have a defect in the skull and therefore no protection to the brain.
The turnaround time is truly the marvel of this technology, where it takes just one machine to do the work of many.
It looks like a Sub-Zero refrigerator, honestly. It's just a big one. It's just a big box with a lot of electronics and lasers. It allows for the production of many parts all at once. So we've done builds that have done 2,000 or 3,000 parts in them, all different.
So what we have here is a three-dimensional build volume.
Production manager Elijah Willis uses computer models based on CAT scans to build the implants.
Basically, one layer at a time, it's going to progress through the build, eventually getting to a point where all the parts are now completed and you have your parts there floating in a bed of powder, which would then start the excavation process.
When OPM was founded in 2000, there were just 3 employees. Now there are 34. Over the next few years, the growth in aerospace is expected to explode as both commercial and military aging fleets are replaced with lighter, more efficient aircraft. For Oxford Performance Materials, that translates into a surge in business, and the company expects to nearly double its workforce to keep pace.
That technology has got the ability to take substantial weight off things that fly. That's really about energy efficiency.
Dave Felice says there are also new orthopedic implants on the way.
We're going to go from cranial to spine to trauma markets. There's just so much opportunity to create value.
Funding for
All right,
Made in Connecticut.
so that's very cool, and we'll see how Oxford Performance Materials does. Does anyone know what this test is? So what are they doing when they shine this structured light on a part? If you want to unmute yourself and chime in if you know. This is a critical test, but what are they trying to do?
Are the spheres, are they like reference points of some kind? Or is that is that something else being tested too?
No, that's a reference point or a reference object. And so what are they trying to do with this reference structured light? So they're trying to measure the exact shape of that cranial implant. Because remember, we talked about you design it in the CAD, right? You print it, but then you need to measure exactly what you made. And so other than putting the, we talked about printing something and then put it in the CT scanner, using structured light is another way to get dimensions of the object. Or if you've ever heard of something called a ferro arm, which is a mechanical way to measure the dimensions of an object. Basically, it traces out critical points and then reconstructs a 3D model of a real object. And so they've just used structured light in this case. And so the ping pong balls are in there in order to make sure that those are spherical, and that's a correction for the object. But they're basically taking pictures of this at the same time that they're shining the light on it, and then they can reconstruct a three-dimensional image. So this is a form of quality control and then feedback to their design in order to correct the CAD models for whatever they want to print. So I wanted to bring that up because sometimes it's called a structured light scanner or a laser scanner or something like that. There's many ways to do this. Ferro arm, CT scanning. There's many ways to reconstruct a digital model of a real three-dimensional object, and that's used a lot in 3D printing to close the loop based on the design. So I just wanted to bring that up. Any other questions or comments on this or aligners or anything like that? Okay, well, you saw that, let me get rid of this and get back to the PowerPoint. You saw at the end of that news article that OPM was interested in aerospace. And so this is from Hexcel, and Hexcel is a big material supplier to the composites industry. So they make things like epoxies, they make things like the foam that goes inside a sandwich composite, they make fiberglass and carbon fiber and all stuff like that. But you see that OPM has really started to get into supplying components for various technologies. So PEEK, or PEKK, whichever variation of PEEK you're interested in, is useful in both biomedical and aerospace, and there are two markets where the barrier to entry for additive manufacturing is reasonable. So they're really OPM is leveraging both their materials technology, because they're traditionally a PEEK maker or PEEK converter, and their 3D printing technology in order to address both of these markets. So that's pretty interesting and a real cool application of polymer additive manufacturing for useful components. Any questions on that? All right, we're going to talk about aerospace in a second. I think that's lecture slide 17, but we just have a couple more bio applications to cover. I think we can get through them today. Again, this is surgery planning and anatomical models. So if you've been to a doctor's office lately, you know that there's posters and there's old skeleton models that were in the old school doctor's offices. Now they have these high fidelity anatomical models, and these were difficult to make back in the day. They were all made by hand. They were all expensive, but now generating anatomical models, and especially generating custom anatomical models for surgery planning or educational purposes is a big business. And so a lot of this is done in PolyJet. That's a big business for Stratasys, and there's also lots of SLA technology involved in this as well. Or if all you have is a material extrusion AM printer, depending on what you want to print and how it's oriented and other issues of shape fidelity, you can at least get rough anatomical models with something as simple as an FDM printer. Another place where additive manufacturing of polymers is contributing to medical technology is in custom surgical instruments. So you've all seen the old school on the TV show or whatever, where they have all these clamps and scissors and whatever surgeons use to do what they need to do. But now with additive manufacturing, surgeons have really started to innovate in terms of saying, I really wish I had a custom this or a custom that, or maybe you need a slightly different size depending on the size of your patient or depending on the surgery that you're doing. And so custom surgical tools, even something as simple as a tweezers or a forceps is something that people are interested in. And of course, since these are made out of plastic, they can be one-time use. They don't have to be made out of stainless steel. They can be made out of different plastics of different stiffness. And so not only making the biomedical implant, but making the tool to do whatever you're interested in is also a viable strategy in biomed. Let's see. We already talked about drill guides and surgical guides. So this is important, especially if you're on the receiving end of the drill. You'd really like that drill to be accurate and not to slip as well. And so these drill guides and these customized drill guides can be made before your surgery. And so these are all ready to go, and it increases positive patient outcomes and makes things easier for everyone. So again, we'll come back to this idea of how do you change business models, and biomedical technology is a big business. And so there's lots of innovation that's possible here. Of course, with COVID, we've seen a lot of innovation in biomedical technology with rapid advancement of these new vaccines and new vaccine technology. But this exists in lots of different areas of biotechnology. And so additive manufacturing has really become one of the important enabling technologies for the biotech and biomedical revolution. And you heard in the aligner, in the dental aligner video, that there's a lot of people in the developed world, but there's a lot of people whose quality of life is increasing quickly. And along with quality of life comes things like dental care, better health care, automobiles, more airplanes, customized products. And so as the standard of living improves over the entire world, a lot more of these custom products and high value products are needed. And so there's a lot of innovation potential for new businesses and things that haven't been thought of before. Oh, this is just an article if you're interested in it, but 3D printing is happening right in the operating room. And eventually the vision is that maybe you'll do 3D printing in situ on a person. This is just a cartoon, so don't get too freaked out about 3D printing right on a person as they're lying on the surgery table. And so this is detailed in this article right here, but it's something to think about and something that folks are thinking about in terms of 3D printing right with living tissue, or 3D printing on living tissue, or 3D printing during surgery as part of the process. There's also some cool 3D printing of drugs. So these are just tablets, but there's a lot of technology in drugs and controlled release. And so the shape of this pill, the powder that's used in this pill, how the drug is distributed within the pill. So mostly tablets like this are just filler, and there's only 10 or 20 milligrams of drug in there. It's not very much. And so additive manufacturing also has a role to play in terms of developing advanced medicines. And then this has been detailed in a number of cases, but one of the first uses of 3D printing in biomedical technology was all the way back in 1997, where they were 3D printing pills. And so there's some interesting news releases on that. And this article right here gives us an idea about all the different biomaterials used in medical 3D printing technology. So if you're interested in metals and metal alloys, if you're interested in ceramics and carbon compounds, if you're interested in polymers and composites, this gives some ideas about whether it's drug delivery systems, tissue engineering scaffolds, dental implants, orthopedic implants, dental fillings. There's some nice sort of guidelines, just like we've seen for other industries, in terms of what technology is used where, and where the opportunities are in the synergy between additive manufacturing and biotech and dental. So the future is something that looks like this. In this PNAS article, they talk about how do you 3D print vascularized tissues. So it's not good enough to just print a big piece of bone like this. There are no big organs, or there's no big pieces of bone in the human body that don't have blood vessels very close by. So the key to this is, how do you make biomaterials with blood vessels or with vasculature in them? Or how do you make a porous material that you can pump blood through? And so this is how the body constructs materials. So there's only a couple layers of cells around every blood vessel. And the question is, you need to print biomaterial. You need to print structural support. And you need to print blood vessel. And this has been a huge challenge for people doing bioprinting, because they can print, let's say, a tissue scaffold that looks like an ear, or they can print a tissue scaffold that looks like a femur, or they can print that cranial implant, and that PEEK cranial implant is meant to just stay in there as an inert piece of plastic. But if you want to print an organ, or if you want to print a tissue scaffold that's eventually going to degrade and become a real piece of tissue, you need to be able to print this vasculature. And so there's been a lot of good work on this in terms of how to print artificial organs, and some of the ways in which to print materials that become the blood vessels. And so this is just one example right here, where they're using two different inks. They have an ink that's going to be the blood vessel, and they have a cellular ink. And so they're able to use this casting and evacuation technology, and then perfusion just means they pump blood through this thing, in order to get the biomaterial shaped with cells, with vasculature, and eventually, if you do this perfusion in just the right way, you get a real blood vessel that's covered in these endothelial cells, and then you have your biomaterial. So there's lots of different ways that people have done this with phase change polymers, with dissolvable polymers, with lots of different materials. And if you're interested in the biomaterial part of bioprinting, there's a lot of good literature out there. And this article in PNAS gives you some ideas. And they've been using this technology at Harvard for artificial kidneys, for artificial livers, in order to do drug testing on, in order to do other types of biomedical testing, where now you don't need a liver from a mouse, or you don't need to sacrifice an animal in order to do some biomedical testing. You can do it on one of these artificial organs that has a similar function to some type of real organ. So this is a boon for biomedical technology, and also increases the environmental friendliness of developing some of these biomedical technologies. And I don't have a slide on this, but people, in terms of 3D printing food and having artificial meat that's starting to become lab-grown meat, how do you 3D print hamburgers? How do you 3D print steaks? It's almost exactly the same process as this. And so that's an innovation if you're interested not only in 3D printing custom chocolates for Valentine's Day, you can think about what's the next generation of 3D printing tissues? What does that look like in terms of food? Any questions on this? Okay, I think that's all we're going to talk about in terms of biomed. I just wanted to cover a couple of these examples, because I know that some of you out there are interested in materials, some of you out there are interested in additive, and some of you out there are working in applications labs where you want to use this technology to do other stuff. And so this is the other stuff part, and additive manufacturing has been making big strides in biomed. let's see, we have a few minutes left. So if you switch over to slide set 17, which is in box here once I find it. So again, we just covered biomed and dental. We're going to talk about aerospace a little bit, and we're going to talk about automotive. And we've got 2 lectures and change to do that. So we'll get as far as we can. But just like we saw OPM or Oxford Performance Materials using PEEK or PEKK in biomed and aerospace, there's a lot of companies that are thinking about using titanium in biomedical implants and in aerospace, or other high-end polymers in aerospace and high-end automotive. But aerospace, because lightness is so prized, or the weight of materials is so important, and the weight of structures is so important in aerospace, that's provided an opportunity for additive manufacturing. And we've covered things like topology optimization. How do you optimize the strength of a structure while taking weight out of it? And aerospace has really used some of these tools. And in most airplanes today, as long as they were built within the last 10 years, many of those airplanes have 3D printed parts on them right now. And so aerospace is only adopting more and more additively manufactured parts as new airplanes are being built. So if we go back to our table, these are some of the advantages. So whether you're doing production of spare parts, turns out that aerospace is small volume manufacturing because there aren't that many airplanes made every year as compared to something like cars or shoes. Complex work pieces are important for aerospace. Machine tools, of course, or we're going to cover an example in trim tools. That's making sure that the airplane wing that you made has the right shape. Component manufacturing and on-site manufacturing is all important for aerospace in various capacities, including rapid repair. The hours that the airplane is in the shop or can't fly is big money to these airlines because they only make money when the airplane is flying. So that's important to consider. And here we go back to this chart in terms of the specific industry. So you see in aerospace, prototyping, component manufacturing, weight is huge. And aerospace also includes the space part of aerospace, so satellites and the space industry, and certainly the private space industry has been having huge wins lately with SpaceX and Blue Origin and other private space companies that are sending both satellites and humans into space. And so that's been a boon industry for sure. Engine components. So those are, there are 3D printed parts in Airbus engines and GE engines. Flight certified hardware, that's a big deal in aerospace. That's a very specific quality control and certification process, and manufacturing of satellites and rockets, etc. So again, the global aerospace industry is worth almost $1 trillion. Maybe it is by now because this was in 2018. And so this is not as quite a big market as automotive, but it's pretty darn big and it's growing, even though there's been some hiccups in the commercial aviation industry this year. Airplanes are still being made, airplanes are still being bought, and that will only increase as the standard of living increases for people around the globe. They want to travel, and they want to travel quickly, and they do more business, and the way that that's done is with airplanes. And so you see some of the applications for AM in both space and commercial aerospace and defense. Remember, there's a lot of the military industrial complex that does aerospace as well. And so current applications, there's a lot of modeling and prototyping that's done. So that's routine with additive manufacturing. But these complex low volume parts, I just heard a talk from General Electric yesterday, and they're printing an entire shroud assembly in titanium using additive manufacturing for one of their next generation turboprop engines. And so that's a big part. It's on the order of 10 kilograms. And so that's a lot of titanium. And if you wanted to machine that out of titanium, it's incredibly expensive. And so they were talking about how additive has been a competitive advantage in producing these components for turboprop engines where they're only going to make 5,000 of them or 10,000 of them. And that is actually low volume compared to making 1 million cars a year or something like that. And so there's been some big innovations in aerospace in terms of low volume, but very complex, expensive material parts. And then they don't like to print, or they don't like to manufacture lots and lots of spare parts because it's expensive. You put them in a warehouse, who knows how they're going to age. And so being able to print replacement parts is really important. And there's a lot of old aircraft out there. The B-52 bomber is 50 plus years old at this point. And so finding replacement parts, especially for old military aircraft and other antique civilian aircraft that are still in service, the only way you can get some of those spare parts is to just print them from scratch. Potential applications. This is really interesting, embedded functionality. And if we get to it, the last lecture this semester will be how do you print sensors into parts, or how do you print other functionality in composite and polymeric parts, because the health of an airplane is all about monitoring and figuring out when something goes wrong. And so there's a lot of embedded sensor technology that they'd like to deploy. They'd like to print aircraft wings. They're already printing complex engine parts, and they would like to do forward deployed printing so they can print in under-resourced environments where militaries operate high-tech equipment. Space, there's a lot of cool space applications out there in terms of printing in space. So I have a picture of that if you've ever seen the Made in Space printers or the news items on that. Printing specialized parts. You know, you only need one Mars rover of one design because you're only going to send one until you come up with a new design. And so people thinking about custom space exploration vehicles, that's an area for low volume manufacturing for sure, or a volume of one. Printing really unique structures using lightweight, high strength materials and minimal waste, that's all important for space. So people are thinking about how do you build habitats, or how do you build the next space station? And the ISS basically was manufactured on Earth and just flown up to space and put together in hundreds of parts and modules. And that was sort of the old way to do it. But one of the new ways people are thinking about is you drop off a concrete 3D printer on the moon. There's lots of raw material on the moon, and you print a structure right there on the moon or Mars. And so Penn State has been part of the 3D printing Mars Habitat Challenge, where basically you have a 3D printer, maybe you have some additives, and then you have to use the local resources in order to print a habitat. And so how do you print large-scale structures up in space is a really interesting challenge and interesting to think about. Okay, any questions on this?
I have a quick question, sort of random maybe.
Sure.
But when you say there's a lot of raw materials on the moon, what exactly is that? Like what?
Oh.
I don't know. Like that, I don't understand that.
Yeah, so there's a lot of rock and a lot of sand or dust on the moon. And so one of the challenges for this 3D printing habitat is if you take that and combine it with something like make a cement and then print that cement, you don't have to bring all of those bricks to the moon, or you don't have to bring all of the concrete to the moon in order to build a base. Maybe you use some of the natural materials because there's a lot of dust, and you combine it with just a little bit of binder and then 3D print it. So I don't mean that there's, you know, lots of water and lots of lime and other things that we traditionally use to make cement, but there's basically a lot of rocks on the moon or Mars, which are the short-term solar system targets. And so how do you make a shelter out of those materials that are sitting there with a 3D printer? That's what I mean.
Oh, okay, thank you.
Yeah, and if you look at some of the Mars Habitat Challenge images, they're basically trying to print habitats out of sand, which is just a very primitive form of concrete. So it's not like things are all set up and ready for us to build wood frame houses on the moon or Mars, but there are some raw materials up there that perhaps we can deploy in additive manufacturing. And so there's just lots of drivers for adopting additive in aerospace, and these are some of them right here that you can take a look at. And we'll talk a lot about this Deloitte model for how additive manufacturing is being adopted in these various industries like aerospace next time. So are there any final questions here? We're a couple minutes over. I apologize for that, but any final questions before we end for today? Okay, well, we're going to keep talking about applications. So if we're not covering something, or if something's not clear, like the Mars Habitat Challenge or something like that, just give me a shout. I'd be happy to discuss it. And make sure you continue to peck away at your final projects and presentations, and I'll put some drop boxes up and give you some final advice on your assignments. So thank you very much, and I'll see you next Tuesday on Zoom.
Thank you.
Thanks.